All right, so today we're going to be looking at solving trig problems in 2 dimensions. So let's start by thinking about the tools we have for solving right angle triangles. So the three primary things we can do is we can use SOHCAHTOA. So remember, SOHCAHTOA is an acronym. Stands for sine of an angle is opposite over hypotenuse, cosine of an angle is adjacent over hypotenuse, and tan of an angle is opposite over adjacent. So we can use that to relate angles and side lengths and solve for information. Another thing we can do that is just the side lengths is if we have a right angle triangle, we can do a squared plus b squared equals c squared. So that's the Pythagorean theorem. That's another option. One important thing to remember is for right angle triangles with Pythagorean theorem, the side by itself, the c squared in this example, is always the hypotenuse, and these two that the squares add, those are the other two legs of the triangle. And the other thing we can do is we can remember that the interior angles add to 180 degrees. And this is true for all triangles, both right triangles and non-right angle triangles. But we're going to start by focusing on right angle triangles. So let's do some examples just using these tools to solve some problems. All right, so it says Jonathan needs to tie a rope from the top of a flagpole to the ground 10 meters away. The angle of inclination from the tie point to the top of the flagpole is 42 degrees. So the first question is, how tall is the flagpole? So in order to envision this and draw our triangle, we're going to draw this out. So we have some flagpole. It's got a little flag on the top of it. And we have some wire that is 10 meters away, it says. So something like this. There's our wire. And it tells us that the wire's tied 10 meters away, and the angle of inclination, which is the angle above horizontal and inclined up, is 42 degrees. It's asking us how tall the flagpole is. So we might call that h or something for the height of the flagpole. Okay, so when we're doing a problem like this, we're going to look at the information we have and try to solve it. So our options are interior angles add up to 180 degrees. We could use that. That could tell us, we know this is a right angle between the flagpole and the ground, so that could tell us this top angle. But I don't know if that's really going to get us closer to finding h, but we could do that. Pythagorean theorem, we need 2 out of the 3 side lengths to do that, so that doesn't look helpful. So we're going to have to use SOHCAHTOA. And for this angle of reference, we want to know the opposite, and we do know the adjacent. So the opposite and adjacent, and tan tells us information about opposite over adjacent. So tan is the trig ratio we want to use. So tan of 42 degrees is equal to opposite h over adjacent 10. And we can rearrange this, so we'll multiply the 10 up, punch that on our calculator. So this would be 10 times tan 42 degrees. And that is going to give us, punch in your calculator, 9 meters, approximately. So this is 9 meters for h. We'll just circle that as our answer. Okay, so the next question is, how long must the rope be? Okay, so if we go to our diagram, the length of the rope would be here, and maybe we'll label that as L. I'm going to label it as a cursive L. That way it doesn't look like a 1. Okay, so how long must that be? Now we have options here. We can use Pythagorean theorem now because we know the two out of the 3 side lengths. We know this is 9, we know this is 10. We can do that. We can also use SOHCAHTOA because we know these side lengths and we know an angle. It doesn't really matter which one we use. I'm going to use Pythagorean theorem here just so we get an example of that. So in this case, the hypotenuse squared is equal to the sum of the other 2 sides squared. So it's going to be 9 squared plus 10 squared and that's going to be 181. So 81 plus 100, 181 is equal to L squared. And then let's square root both sides. Square root, and we get L is approximately 13.45-ish meters. All right. So that's some ways we can use right angle triangles to solve these questions. It's questions like this. All right, let's move on to non-right angle triangles. Okay. So one thing that's important to remember when we're working with non-right angle triangles is we have a convention for labeling the vertices or the angles and the side lengths. So I'm just going to draw a triangle. We're going to say it's not a right angle triangle. It might be, but it's not important. And we're going to label these sides. So this is side A, B, these angles, and C. And we always label the angles, or the vertices, the corners, with capital letters. And we label the side lengths with lowercase letters. And it's important that we use the convention that the capital letter A, the opposite side length, is going to be a lowercase a. Capital letter angle B, opposite side length, lowercase b, and C, lowercase c. So the side length and the angle are always opposite each other. That is important. Okay, so we have some tools we can use that you would have learned in grade 10. So there's sine law and cosine law. So the first we'll go over sine law. So there's kind of two versions of sine law. They're the same, but they're just rearranged a little bit. This one here, we do sine angle A over side length A equals sine angle B over side length B is equal to sine angle C over side length C. Okay, this one's really good for finding angles because all the angles are on the tops of the fractions and it makes it easier to rearrange. And whenever we do this, we only need to use 2 out of the 3 pieces of this equation. So if we know stuff about A and C, we can just get rid of the B and do sine A over A equals sine C over C. The other version we have is just the flip of this. So it's where we put all of the side lengths on the top. And this one's just a little bit easier to find the side lengths. So it's A over sine A equals B over sine B equals C over sine C. Okay, and this is the same thing, it's just flipped upside down. So remember the angles, all these are capital letters. The angles are always in the equations. And in reference to a triangle, the side length and the angle are always opposite each other. Okay, next we have cosine law. So cosine law is actually a special version of, or an extended version of the Pythagorean theorem. So a squared equals b squared plus c squared minus 2bc cosine capital A. So these are, you'll note that this has all side lengths except for the angle, and the angle is opposite of the side length we want to find. So this is really useful if we know all 3 side lengths and 1 angle. Or sorry, 2 side lengths and an angle, and we can find the 3rd side length. So in that way it's similar to Pythagorean theorem, but we need to know an angle as well. And we can rearrange this to solve for the angle as well. And that looks like this. Cosine of the angle is equal to b squared plus c squared minus a squared over 2bc. Okay. One important thing to talk about when we're talking about cosine law is the letters here don't need to stay consistent. But what does need to stay consistent is, say we want to find side length B, we don't try to rearrange this. We just swap say the A's and the B's or something like that. And we don't always use A, B, and C to label our triangles. We might use other letters. What's really important here is that the side lengths we're trying to find, this is its opposite angle. Okay, well, so we'll see that when we do an example. Okay, so let's try an example. So with all of our examples, we're always going to read it and try to draw a diagram first. Okay. So the radar screen at an air traffic control tower shows a red airplane 15 kilometers from the tower in a direction of north 40 degrees east. So we'll talk about what north 40 degrees east is if you're unfamiliar with how that angle measurement works. Okay. A blue plane is 16 kilometers from the tower in a direction of north 30 degrees east. If the two aircraft are less than 2 kilometers apart, the aircraft controller, Cindy, must report it. Should Cindy report it? So we need to figure out how far apart these two aircraft are. So let's start with a diagram. So we're going to draw a compass. So we're going to take a bit of space here. I like to have nice big diagrams. Okay. Now most of the stuff here is happening in the northeastern quadrant, which is this top right quadrant. So I'm going to skew my compass a little bit. Okay, so on a compass, north, east, south, west, and the aircraft control tower is at the center of this, because that's the perspective we're taking here. So it says the red airplane, so I'll use a red line, is 15 kilometers from the tower in a direction of north 40 degrees east. So north 40 degrees east means we're measuring from north 40 degrees towards the east. So that would be somewhere over here. And this is 40 degrees. I'm going to have to label it outside because it's a little tight. Okay, and this is 15 kilometers. We'll just label it as 15 and know we're working in kilometers. Okay, a blue airplane is 16 kilometers from the tower north 30 degrees east. So north 30 degrees to the east. So that would be a lesser angle. We'll exaggerate the lesserness of it a little bit. And this is 16. And this is 30 degrees. And the question is, how far apart are these? So how far apart are these two airplanes? And that would be this. So maybe we'll label this X for the distance between the two airplanes. Okay, so we definitely have a triangle here. It's red, the blue line, and the green line form a triangle. And we have two side lengths. And we have some information about the angles, but we don't actually have an interior angle of our triangle yet. So we're going to need to find that. So if this blue line's 30 degrees from north and the red line's 40 degrees from north, then this angle between them must be 10 degrees. Okay. And now we have a triangle with enough information that I think we can try to find something. So let's think about what formula we want to use. Do we want to use sine law or cosine law? So the general rule of thumb is sine law is a lot easier to work with. But for sine law, we need to have a side angle pair, or some people call it opposite information. So we need to have a side and its associated angle, which is opposite of it. So side angle pair. Side angle pair. So blue would match up to this angle over up here. Those would be a pair, which we don't know that angle. And the red would match up to this angle, right? Because remember, they're always on opposite sides. So we don't have any pairs. So we can't use sine law. But we can use cosine law because we have two of the side lengths, and we have the angle opposite of the unknown. If we look at our formula, the angle A helps us find side length A. So in this case, the angle opposite of x will help us find it. So this is the formula we're going to use. We're going to use cosine law. So we will find x squared is equal to the other two sides squared, 15 squared plus 16 squared minus 2 times 15 times 16. So we're just plugging everything in. Cosine the angle opposite of the thing we're trying to find, which in this case is 10 degrees. Okay, and at this point, you're going to need to punch that in your calculator. You can do it in more than one step, or you can try to do it all at once. It's a bit of work. And I get that that is approximately equal to 8.2922. So that's x squared. So note that that's x squared. That's not actually the length of that side. Okay. We still have to square root both sides. So we'll square root both sides. And we get x is equal to approximately 2.9. And we were working in kilometers, so this is in kilometers. All right. So we still have to answer the question, should Cindy report that these two airplanes are too close to each other? So it says she has to report it if they're less than 2 kilometers apart, and they are more than 2 kilometers apart, so she does not need to report it. So therefore, Cindy does not need to report the aircrafts or the airplanes. All right. Let's go to the next question. Give me one moment. Okay. So, a ship at sea on a foggy night observes the lights of two other watercraft in the fog. The angle between the lights is 35 degrees. And it can confirm with radar that the leftmost watercraft is 4.6 kilometers away. The rightmost watercraft isn't showing up on the radar, but through radio contact, you are able to confirm the distance between the two other watercraft is 3.6 kilometers. How close is the unknown watercraft? Okay. That is a lot of like numbers and information that's so hard to visualize. We're going to need a diagram. So let's draw a diagram. Let's draw the ship. This is us, our perspective. Okay. And it said we have two boats forming a 35-degree angle. So let's draw two lines going 35 degrees apart. 35 degrees. Okay, let's label this one boat A, this one boat B. All right. Now it says the leftmost one is 4.6 kilometers, so that'd be the leftmost here, so 4.6 kilometers. And it says the other one's not showing up, but the radio contact is able to confirm the distance between the two other ones, so this distance is 3.6. How close is this unknown one? So we want to find A. The big question is, what is this side length here, which would be A, the opposite of angle A? Side length A to our triangle. Okay, well, let's think about what we have and what we need here. So we do have two side lengths and an angle, so maybe we could use cosine law. But remember, cosine law, we need the angle opposite of the unknown. We don't have the angle opposite of the unknown. That'd be up here. And this is not a right angle triangle, so we can't say that these have to be adding up to 90 or anything like that. Okay. So I think we're going to need to use sine law. And if we use sine law, we do have a side angle pair, and we have one other side, and it would help us find angle B over here. So we're going to be trying to find angle B, and that's not our answer, but the more information we find about the triangle, the easier it is to solve everything and find the final answer. So once we find this angle, I think we'll be able to go to the next step. So we're going to try to find angle B using sine law. So we'll write sine of angle B over the opposing side length. Remember, it's sine B over B over 4.6 equals sine of the angle here, so sine 35 degrees over 3.6, its opposing side. Okay, So we're going to need to rearrange this a little bit. So we can punch this in our calculator, multiply 4.6 up. And if you do that, you get sine b is equal to 0.7329 something, dot, dot, dot. Okay. Now, excuse me. Normally, we just punch this in our calculator. Inverse sine, find the answer. However, we have been learning about that when we are solving sine of an unknown angle equals a number, there's two possible answers between 0 and 180 degrees. Or between 0 and 360 degrees. Now, normally, that's not a big deal. But with sine, remember with the cast rule, sine, both the angles, if sine's positive, both the angles are between 0 and 180, and they're both possible solutions in this triangle. Okay, so this is called the ambiguous case of sine law. Okay, the ambiguous case of sine law. Okay, what does that mean? It means that we must always find both angles for sine law between 0 degrees and 180 degrees. Okay. So we're going to do that. We're going to find both the possible angles that this gives us. If we're solving for a side length of sine law, we do not need to do the ambiguous case. There is no ambiguous case. There can only be one side length. When you're doing angles, though, we get something like this. We got to find both. So let's draw our diagram. So where is sine positive? Okay, well, sine is positive in the top right two quadrants. And we can find our reference angle. Ref angle is equal to sine, oh boy. Let's write the word sine correctly. Sine inverse of 0.7329. And if we punch it in our calculators, we get that's about 47 degrees. Okay, so these two angles are 47 degrees, and that will be one of our options. So angle B is 47 degrees, or it'll be this angle, the angle between the positive x-axis over to here, and that would be 133 degrees. So there's two possible angles that we could get. Now let's see how this works. So one thing to note, and we'll see this on the next question as well, is sometimes the larger angle, the angle between 90 and 180, is impossible. So in this case, we have 133 degrees here and a 35 degree. We'll still be able to find an angle for A, but sometimes we won't. 47 degrees, the acute angle between 0 and 90 will always give us a possible solution. So we're going to split this up into two halves. So we're going to solve both versions. There's more than one answer. Okay, so this next part, you do not necessarily need to do an amazing diagram, but I'm going to try to draw this. So I'm going to redo our diagrams. So we have our 35 degrees from before with the ship in it. Okay, we found this is 47 degrees. 47. We know that this is 4.6. A, B, 3.6. And if that's the information we have, then we can do 180, find this angle A by doing 180 minus. So 180 minus 35 minus 47. And that gives us 98 degrees. And now we can find angle A. Sorry, side length A. We found angle A. Side length A over its opposite, sine 98 degrees, is equal to, it doesn't matter which ones we use. I'm going to give the ones that were given, use the ones that were given in the question. So 3.6 over sine 35. We rearrange this. We'll multiply the sine 98 up. And we get A is about 6.2 kilometers. Oh, excuse me. Let's check the other one. So this one's a little more awkward to try to redraw the diagram. So we still have our 35 degrees. Whoops. And you can just draw a triangle like this and just label it, and it'll be very inaccurate. But I want to show you what it more or less looks like. So this one's 35 degrees. If this one has a 133 degree angle, it's going to be very open, maybe like that. And this line is still 4.6, but now this side length is going to end up being very short. This angle here, that's our 133 degrees. This is our 3.6. And this will be 180 minus 35 minus 133 is 12 degrees. Okay, so it's still the same problem though. So we want to find A. This was angle A up here, so, angle B over here. This is the ship. So side length A over, in this case, sine 12 is equal to 3.6 over sine 35 degrees. We'll calculate this, multiply sine 12 up, and we get A is equal to 1.1 kilometers. Okay, so we got two answers. And the question often is, which one's correct? And the response is, we don't know. And that's one of the natures of certain questions. And it has to do with the information we were given at the beginning of the question. The information at the beginning was not enough to give a answer. It was enough to give two scenarios, either of which is possible. So if we wanted to know where that boat is, it can't be at both spots at once, then we would need additional information. Okay, and that's what this word ambiguous. The ambiguous just kind of means unclear. It's not discernible, like perfectly discernible. So we can't know exactly which one is correct, so we have to find both answers. And lastly, we're going to just write a conclusion. So it's therefore, the boat is either 1.1 kilometers or 6.2 kilometers away. All right. One last question. Alice, Bob, and Eve are standing on a soccer field. Alice and Bob are 23 meters apart. From Alice's point of view, the others are separated by 52 degrees. Bob and Eve are separated by 27 meters. What is the angle between Alice and Bob from Eve's perspective? Okay, so let's draw a diagram. So let's do A for Alice, B for Bob, and E for Eve. And we'll draw a triangle. No idea if this is an accurate representation of the situation or not. It's not that important. But let's start labeling things. Alice and Alice and Bob are 23 meters apart. So 23 meters. Alice's point of view, that's the angle at Alice. These two are separated by 52 degrees. Bob and Eve are separated by 27 meters. So, what's the angle between Alice and Bob from Eve's perspective? So it's asking us to find the angle E. So that is, maybe we'll just write that's angle E. Okay. So do we use sine law or cosine law? Well, we do have a sine angle pair, and we have the side length opposite of the one we want to find. So I think we can use sine law. So we can get sine E over its opposite, 23, is equal to sine of 52 degrees over its opposite, 27. Okay, and we're finding an angle using sine law. We're going to have to check for the ambiguous case. So we'll rearrange this. We get sine of E equals 0.67126 dot 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 dot. Okay, so we're going to have to check the ambiguous case. Let's draw our diagram. Sine is positive in the top right two quadrants. Our reference angle is the inverse sine of 0.67126. Punch it in our calculators, and we get about 42 degrees. So 42 degrees. 42 degrees. So that means angle E is equal to 42 degrees, or this angle here, which would be 180 minus 42, is 138 degrees. Okay. So we have two possible angles, but look at 138 degrees. Would that work in our triangle? And the way to check is to see if I had a 138 degree angle here, would I be able to find the remaining angle? And we could try that. So we can do the remaining angle would be 180 minus 52 minus that 138 we just found is negative 10 degrees. Okay, well that's not possible. We can't do that. We can have a negative angle in our triangle. We can have a negative interior angle. So that means 138 isn't possible. So sometimes the ambiguous case of sine law will give us two answers, but one of them could be thrown out. So 42 degrees is the only angle from the ambiguous case that works. So let's write that explanation down. So note 138 degrees is impossible. Because 180 degrees minus 52 degrees minus 138 degrees is negative. We can't have a negative third angle. Okay, so that means the only possible answer is the 42 degrees. So therefore, the angle at Eve is 42 degrees. All right, that's it.